Good morning, almost afternoon. Welcome. It's a pleasure to be here, and as you know, it's a challenge to give these lectures with a mix of newcomers and pioneers and experts of the subject, but I'll try. While we're all here interested in mixing, I want to emphasize another aspect of Markov chains, which is closely related to mixing, which is and has some geometric nature. So we're going to look at the Markov chain we'll look at will be sometimes a lazy, simple random walk on the graph. So we have some underlying graph. Simple random walk goes from a vertex to one of the neighbors with equal probability. A lazy simple random walk just stays in place with probability 1/2, and with probability, the remaining probability 1/2 goes uniformly to one of the neighbors. So that's a special case of a lazy Markov chain, where lazy Markov chain, we just want that the probability to go from x to x is at least 1/2 for all x. So that will be a useful thing to avoid periodicity. Most of the chains I'll talk about will be reversible, so this will be satisfied for some measure pi on the state space. And simple random walk is, of course, reversible with when you can take pi of x to be the degree of x, and this will be satisfied if p is either simple random walk or lazy simple random walk. So when we look at the graph, a very large finite graph, and we are interested in mixing, so getting close to the stationary distribution. Well, one obvious obstacle to mixing is has the particle, the random walk, had enough time to escape from the starting point? And so suppose our chain is indeed a simple random walk, or more generally, just a walk along the edges of this graph. So we could also generalize to have a weighted random walk. Then one bound for the mixing time will be the half the diameter of the graph. So let's recall the basic definitions of the subject. So we're looking at the total variation distance between two measures. So that appeared already, and so that's the maximal difference of probabilities. We will look at the distance at time t to from the stationary distribution is the maximum over the starting point of the distance of the distribution at time t. So this is a measure you have starting from x at time t and to this stationary distribution. So here, in this form, I'm using the normalized stationary distribution. So here, when I wrote pi of x equals degree of x, that was not normalized. So if we'll have to normalize it by, well, some normalizing constants, twice the number of edges to apply in this formula. So, and then the mixing time, t mix of epsilon, is the first time, so that d of t is less than epsilon. Another notational thing, d bar of t will be the maximum over all pairs of starting points, x and y, of the distance, total variation distance, between ptx dot and pty dot. So in other words, you don't look at one distribution and compare it to the stationary. You look at the distribution starting from two different starting points and see how far they are, and maximize over these starting points. And on the one hand, the triangle inequality tells you that d bar of t is less than less than twice d of t. This is just the triangle inequality with respect to this norm. And on the other hand, different application of the triangle inequality or convexity tells you that d of t is less than d bar of t. The distance, this is, after all, pi. If you average pt of y dot with respect to pi, you'll get back to pi. So this, so this can be seen as an average of these. So d of t is bounded above by d bar of t, but it's not very far from them. Now, so often in looking at mixing times, often d bar is more convenient, but because of this, they're roughly equivalent. So what you see here, if I fix two starting points, say, call this A and call this Z, then I see that if my time t is less than diameter over 2, so capital D is going to be the diameter of the graph, so it's the maximum over all, say, all choices of A and Z of the distance between A and Z, the graph distance between A and Z. So if t is less than half the diameter, then it implies that this function we defined before as d bar of t is going to be 1. If right, because if we take A and Z, which are a distance which is the diameter, then at time which is less than d over 2, the distribution starting at A and the distribution starting at Z will have disjoint support. So their total variation distance will be maximal, which is 1. So in terms of mixing times, if epsilon is less than a half, then you get the t mix of epsilon is certainly at least d over 2. Now, there are some cases where this bound is sharp, so expander graphs, but these are rather atypical, and a better number to think of for the mixing time is the square of the diameter. And part of what I'll do in these talks is give you some evidence for why the square of the diameter is what to look for, and there are various perspectives on that. So one is actually in some work of Percy and Laurent Salov-Coste on groups of moderate growth. But I want to talk about some other perspectives. In particular, one bound we'll see is that if we have t mix of epsilon is going to be bigger than diameter squared over some constant, 16 log n. And this is for lazy or lazy simple random walk, or also for just simple random walk on an n-vertex graph. If n is large enough, so just depending on epsilon. So this is a very general bound on any graph. So diameter squared gives you the right, a good lower bound up to a log n, and we'll also see some cases where you can get the diameter squared upper bound. Certainly, it's not universal, but there are many cases. So that's one thing we're going to see today. So the emphasis will be on the connection between mixing, spreading in the graph, and actually just getting away from the starting point. And as the simple bound I started with indicates, well, getting away from the starting point is some necessary condition for mixing. It's not sufficient, but we'll explore how close these things are. So in that in mind, let's just first take a look at this function, the distance, distance from x0 to xt, as a function of time. How does this behave? Does this always grow? Well, certainly it can fluctuate, so let's look at up and down, it's random, so let's look at expectation. Again, if we have a single edge, we're going back and forth, so of course it's not growing. So let's look at even times to get rid of, or we could look at either even times or lazy chains to get rid of this periodicity. So let's do even times. So what about this expected distance? Is this growing? Well, certainly still the answer. Well, intuitively we already feel, well, this might be growing, but the point is distance is not a priori a very good controller of the random walk. So if we have, suppose I have a binary tree, and to make a simple example, I'll just make every edge have a very high multiplicity. So I'm walking along this tree. Here the expected distance certainly grows, but now I can change the distances by just connecting. So I can connect this vertex, say, to all vertices at level 100, but these connections will be very weak, a single edge, while all the edges in the tree I'm going to replicate 1,000 times. Okay, so each edge here is replicated 1,000 times, and I have these weak connections, but the weak connections are only to vertices at distance 10, or distance 100 away, and we repeat this. So we have these weak connections at distance, which are, so everything at distance 100 from the root is connected to everything at distance 200, 200 to 300, and so on. So these weak connections are not really affecting the random walk much, because remember, the edges of the tree have multiplicity 1,000. So when we are choosing uniformly, the chance we'll choose one of these dotted edges is very small. We have a choice of 3,000 undotted edges and one dotted edge at most. So they're not affecting the random walk much. But if we're looking at the distance, at least for quite a while, we'll see this kind of periodic behavior. The distance is going to grow, and then as we reach 100, suddenly the distance is going to drop to 1. So it looks like distance has almost nothing to do with the actual behavior of the random walk. We'll see that's not quite the case. So one thing that makes this example, this counterexample work, is that we looked at the special starting point. And I told you about this tree. We're going to, if we want a finite graph, we'll truncate this at some distance. So this root is a very special starting point. So let's try to avoid the special starting point, either by taking a random walk on a group where all starting points are the same, or still staying more general, let's think of x0 started according to the stationary distribution. So instead of looking, and here in this expectation, we're going to take averaging also with respect to the starting distribution. So maybe I'll write e pi to emphasize we're starting according to pi, and then looking at the distance. Now it really seems like this should be growing. It's harder to come up with a counterexample, but it's not still. Here's a nice simple example due to Oded Shram, and it goes as follows. Let's start with the cycle. And so this is a cycle with n nodes. We're going to again replicate every edge many times. Let's take every edge and repeat it 2 to the n times. Okay, so this is true for all the edges of the cycle. And then we're going to add some of these single edges. And how are they going to be added? From every vertex, we're going to connect to all nodes that are distanced at least root n on the cycle. So this is distance root n. So we don't connect to kind of the neighbors on the cycle, anything at distance root n. We connect to anything which is far away on the cycle, distance bigger than root n, by this kind of weak edge. Okay. Now look at this graph. how does the profile of the distance behave? So look at so notice that this graph is transitive. In fact, it's a Cayley graph. All starting nodes look the same. So when I write, I can think of e pi or just fix the starting point. It doesn't affect this profile of the distances. So how does this distance behave as a function of t? Right, 2t. So first, for t equals 0, distance is always 0. Now, if t is, say, about order root n, how is the distance going to look at time? If t is, say, root n, then the random walk still hasn't, it hasn't gone to distance root n yet. And so it's somewhere here. What's the diameter of this graph? Anyone tell me? Again, I emphasize, for every vertex, I connect to all vertices. So I drew this, but remember, this is true for every vertex. I'm connecting to all nodes that are further on the cycle than root n. Diameter is 2, right? From any two nodes, if their distance on the cycle is bigger than root n, I go in one step. If the distance is less than root n, I can just go far away and then come back. Okay, so this is a graph of diameter 2. Okay, so the cycle has length n, but the graph with these additional edges has diameter 2. So, so the distance here will be about 2. So the expected distance is 2 up to a negligible correction. We might still be at the starting point, but that's unlikely, or right in the neighbor of the starting point. And most likely we're somewhere here where the closest distance is just to make 2 steps. But then if I take time, which is, about the mixing time of this, say order n squared, at time n squared, I've spread roughly uniformly on this whole cycle. Remember that all the edges of the cycle have been replicated 2 to the n times. So what this means is by time n squared, I'm extremely unlikely to use any of the red edges, because for every vertex, every vertex sees about n red edges and 2 to the n black edges to the neighbors. So by time n squared, it's extremely unlikely to use any of the red edges. So, so by time n squared, I'm still only walking on the cycle. Time n squared, I'm spread uniformly on the cycle. So with high probability, I'm one of these. Most vertices are far from the starting point on the cycle. Their distance in the cycle is bigger than root n. So I get, so the distance in the graph is just 1, except for a tiny correction, little o of 1. So it's gone from 0 up to about 2 and then down to about 1. And as n gets to infinity, you get a distance dropping down by a factor of 2, even though we're walking in a transitive graph. Okay. Now that you see that, well, can you build an example with the factor of 4? Maybe some product, that's what I was thinking. But actually, 2 is the most the distance can drop. Can't drop by more than 2. And let me show you, before getting to the more heavy mathematics, show you a very cute argument to prove that due to Mark Braverman. He never wrote it down, but he did tell it to me over lunch. So since it's almost lunch, I'll replicate that for you. So what do we want to do? We want to compare the distance at. So we're just going to look at even times to avoid the periodicity. And we're going to use, so what is the statement? We have a reversible chain. X0 started according to pi. Then the expected, so pi is this reversing measure up there. The expected distance from x0 to xt is at least, 2t, is at least half the expected distance from x0 to xs, provided s is, right, so we're talking about s less than t. So here's the proof. So we start x0, we start according to pi, and now we're going to walk for t steps. So this is, just the time axis. I'm not drawing the graph. And then here's the interesting device at time. Okay, so this let's walk all the way to. So we have this time x2t. To do this, and I want to have particle split. Okay, let me draw this. XS. So let's see if this is going to be good. So we have x2t here. At time s, I want the particle to split to 2 copies. Yeah, so this will work. So we start a random walk at x0. At time s, the particle doing the random walk splits to 2 independent copies that continue walking independently. So I draw this way. The particles might decide to continue walking along the same edge. This is just a time diagram. It's not, then it's going to be mapped to the graph. But what it depicts, so we have a particle. It walks until time s, and then it splits in 2 copies. One I'm continuing to call, this is xs plus 1, and so on. The other one I call xs plus 1 tilde. So it's just an independent copy. From xs, I run in 2 independent copies of the chain for another, 2t, 2t on the bottom. So, yeah. So let me no. So this is 2s. This is 2s. This I run to 2s. This I run to 2t. Okay. So okay. So this is the picture. Now let's look. Is it clear what happened at this point? I'm not drawing on the graph. At this point, a particle walked until time s. Then it split in 2 copies, like an amoeba. And these 2 particles continued to walk independently, one for another s steps, and one for another, 2t minus s steps. Okay, now let's write down the triangle inequality. So d is now, distance. So d of x0 and x2t tilde is at most, sorry, I want to write it this way. The distance from x0 to x2s is at most the distance. So I want to go from here to here. Well, I can go from here to x. to xt tilde and add the distance from x to s to x to t tilde. Right? This is just a triangle inequality. Now take expectations. So this is what do we have here? Now the distance from x0 to x2 t2 tilde is just what we want. The tildes don't matter when we take expectation. We're just going to get distance from x0 to x2t. Remember that x0 was started uniformly, pi. Now what happens here? If you start x0 at distribution pi, x2s also has distribution pi. And reversibility just means that if you start according to pi and you move forward in time or backward in time, you just have the same distribution. So this path going from x to s until xs, so this is going back in time here, and then switching gears and walking along this path, xs plus 1 tilde, up to x2 tilde, is just another copy of the random walk, started at a stationary point, x to s is a stationary point, and run for the same time. So what is the total time? S steps here, and another 2t minus s steps here. So this expectation is just going to be the same expectation of distance of x0 to x2t. The expectation of this is the same as the expectation of this, when averaged according to the stationary distribution. Okay, and we're done. This is just twice the same thing, and that's the inequality we have over there. So distance can't go, expected distance can't go down by more than a factor of 2.
Next to it, 2s. And your result, big will stay.
Yes, thank you. Sorry, 2s. Thanks. Okay, so that's something about distance. Now I want to get to these mixing inequalities. I guess I can use the other board. And the key element of this mixing inequality is the that I wrote related to the diameter squared over log n, is the Varopoulos-Karn inequality, which says that for reversible Markov chain, if I look at the probability in t steps to go from a node A to a node Y, that's bounded by twice. Okay, this is some unimportant correction constant. Well, it has to be there, but the important part is e to the minus distance squared of A and Y over 2t. Okay, so why does that prove the inequality? The inequality on mixing times. So I should say Varopoulos proved a weaker version of this, slightly weaker, using an amazing proof, which was based on taking the graph, turning the edges into little pipes, thinking of Brownian motion on the resulting manifold, bounding that, and getting back to the random walk. And then Karn used some ideas of that proof to transform to a understandable kind of direct proof in the graph setting, which I'll show you soon.
Now, is there an x on the left-hand side? What's x?
Oh, x is A, sorry. Thank you. Thanks. Okay, so let's see how do we use that for mixing. So we have, right, we have the graph. We mark two vertices A and Z, where the distance of AZ is the diameter of the graph. And let's take a set A, which are all vertices Y, so that the distance from A to Y is, say, at most diameter over 2. And observe that this is contained in the Y's so that the distance from Y to Z is bigger than d over 2. Right? That's just triangle inequality. Now, now if we want to bound, what is the probability starting from, say, z of being in the set A? So the set A are vertices that are, distance less than diameter over 2 to little a. So how can we bound this probability? So we have to sum over y and a, the probability to go in t steps from z to y. This probability, we throw in that bound. Now, how big could this ratio be? In a graph, remember, pi are the degrees. So the maximum ratio of degrees that could happen is n. So we can write 2 root n for that factor. Now we have e to the minus distance squared, but now we're looking at distance squared from z to elements of A. That distance squared is, the distance is at least capital D over 2. So we get d squared over 8t. Okay? D over 2 squared divided by 2t. That's what we get. And, okay, now if, right, so if you take now little t to be bigger than that number over there, so d squared over 16, I'm sorry, if t is less than d squared over 16 log n, but we want to show that in times like that, you can't mix, and that means that the mixing time is bigger, so the total variation distance will still be large. Well, let's estimate what is this probability at that time, so we plug in this. So this factor here, for this, it's going to be at most 1 over n squared, right? If you plug in this value of t. So we get overall, so we get 2 root n times n over n squared. In other words, 2 over root n is an upper bound. Okay, please stop me if there's something unclear. Right, the size of A is at most n, so we just use that. Now, the same argument tells us that the probability to go from little a to the complement of the set A is at most 2 over root n. That's just the same argument. So the probability to go from little a to A is bigger than 1 minus 2 over root n. And so the total variation distance of PTA dot and PTZ dot, the distribution starting from T and A, is going to be at least 1 minus 4 over root n. So you see that for n large, this is going to be large, and that gives you this bound on mixing time for epsilon, for epsilon less than a half, because we have to go from this d of t to the d bar of t. This is measuring the distance from 2 different starting points and showing that the distance from when we have 2 different starting points, the distance of the distributions is large, right? This just tells us that this is going to be, d bar of t is going to be at least this. And so we easily get that inference. So that theorem there is for epsilon less than a half, and n has to be large enough. Any questions? Okay, so you already see one use of this inequality. This inequality was, again, the first proof of it. The motivation was not to bound mixing times on finite graphs. The motivation was to understand actually long-range estimates for random walks on infinite graphs. So what we're applying here is a principle I learned from David Aldous, which is the infinite graph is an excellent warm-up for the large finite graph. And we want to prove this, but in order not to be bogged down by notation, let's first observe that to prove this, so this inequality is useful in infinite and in finite graphs. But to prove it, it's enough to prove it for finite graphs, because I mean, I'm only going to look at at finite degree graphs. So I'm not going to allow any vertex to have infinite degree. And so, if I'm just walking to distance t, the number of vertices at distance t from A is finite. So I can just, everything that's distance bigger than t plus 1 from A, I can just remove, and I'm not affecting the behavior of the random walk in the first t steps. So to prove this even in an infinite graph, it's enough to prove it in a finite graph. Now I'm going to make some simplification in the proof. So I'm going to prove it to you for the case of pi, which is constant. So you can think of simple random walk on a regular graph. This is an important special case because this is useful for random walks on Cayley graphs. So pi, which is uniform measure. And the only difference is we're going to write down some scalar products. And when you work with the general pi, you have to do it in the space, the inner product space L2 of pi, rather than just straight L2. And but it's just straightforward in the generalization to prove the general case. So let's do just the special case here. Pi equals constant and the Markov, the state space finite. It's still a very nice proof. You'll still see the idea of the general proof. It's a small modification. Let me advertise that in my book with Russ Lyons, we have an exposition of this probability on trees and networks. We have an exposition of this also in the general case, or you can look in the original Karn paper. OK, so to prove this, how are we going to relate the distance to the to this power? So the key idea, which I won't have time to fully motivate, is to think of this p to the t ay as some polynomial, the tth power, applied to p. So we think of so we are looking at p of ay. So think of p as a matrix, and we want to look at this matrix, take it to a power t, and apply it to a point ay. So this is a special case of taking some polynomial q, applying it to p, and looking at an entry ay of this. So the fact that a and y are far away means that if I take q of p, which is of the form p to the t plus some correction, some aj p to the j, and this, but this j is going to be less than the distance from a to y. Oh, I don't want to write aj, bj. So I have some polynomial correction to this high power, but I'm just going to correct it with powers that are smaller than the distance. This doesn't have any effect if I then look at the ay entry of this, of q of p. Q of p, for this choice, when applied to ay, is going to be the same as p to the t ay, because this kind of low-degree polynomial, when applied to points ay that are so far apart, just going to give me 0. So with that motivation, we have a high power we're interested in. We are allowed to make low-power corrections in trying to get something small. So anyone here who comes from analysis might guess, if I want to approximate a high-power polynomial by a low-degree polynomial, what kind of ideas come to mind? Which polynomials? Chebyshev. Right? So that's going to be the motivation. But we don't actually, so we're going to use Chebyshev polynomials. We're just going to use their definition. So we don't need explicitly to use any theorems on best approximation. We'll see how the definition is powerful. So what is the Chebyshev polynomial? Remember, qk of cosine theta is cosine of k theta. That's what defines these. So usually they're called tk. I'm just going to call them qk. So just because of the identity cosine k plus 1 theta plus cosine k minus 1 theta equals 2 cosine theta cosine k theta, writing it in terms of these, what is this saying is qk plus 1 of x. So let's write x for cosine theta. So qk plus 1 of x plus qk minus 1 of x is 2x qk of x. Now if you take this and move it to the other side, you see by induction that indeed these are polynomials. So q0 is just identically 1. q1 of x is x. q2 of x is 2x squared minus 1. And qk is a degree k polynomial. So you just see this by induction from this, right? You move this to the other side, and you see qk plus 1 is 2x times qk with a lower order correction. So indeed, the degree increases by 1 every step. So it's degree k. And we also need the observation that qk of x has absolute value less than 1 for all x in minus 1, 1. OK, so if you write these out as polynomials, you don't see that. But if you go back to the definition, well, you do see it. Right? So if x is minus 1, 1, it can be explicitly written as cosine theta, and then we know this. So how are we going to use that? Suppose we're now going to take P to be a symmetric. So P will be our random walk, which it's going to be so P is a symmetric matrix. And for a Markov chain, all the eigenvalues are between minus 1 and 1. So all the lambda, the eigenvalues, are in minus 1, 1. So if you look at qk of P, it's also going to be a symmetric matrix. Right? If you just take P and diagonalize, you take qk of P, it's just going to be obtained by applying qk to the eigenvalues. Now, what's the norm, the L2 norm of a symmetric matrix? It's just the largest eigenvalue in absolute value. So if I want the L2 norm, right, for symmetric matrices, spectral radius and norm is the same. This is the norm, the operator norm of the matrix. So how much it can grow norms of vectors. It's just the largest eigenvalue. And because all the eigenvalues of this are just the qk of lambda, where lambda is eigenvalue of P, lambda is in minus 1, 1, eigenvalues of P are in minus 1, 1. So qk of lambda is also going to be in minus 1, 1. And so the norm of this, which is the largest of these, is at most 1. Here we're going to need that. Another thing we're going to need is that if we take qk of P, so this is a matrix, an n by n matrix if we have a graph of size n. And let's look at the ay entry of that. So A is one vertex, Y is another vertex. This is going to be 0 if k is less than the distance from A to Y. Why is that? Because qk of P is a polynomial of degree k. So we're just adding powers of P that are at most k. So P to the k from A to Y is 0. You can't get from A to Y in k or less steps. So this is just adding zeros. So this is 0. Okay? This is what we want to use. Now, this is supposed to be a conversation, so if anyone has questions or I've skipped something, please tell me. All right? So now, we only started the proof, but it turns out we're almost done. So we're going to need the binomial expansion next. So let's write x, which is cosine theta. Let's write it as e to the I theta plus e to the minus I theta over 2. And now let's look at x to the t. So, well, it's this thing to the t. And now, we can write out the binomial expansion. I want to write it in terms of a simple random walk. So So if you write this, the binomial expansion, then you can rewrite it in this form where this is ST. ST is a simple random walk on just the integers. Even without the binomial expansion, you can think of this explicitly as write out t factors like this, and each time you pick out, here I'm going to take e to the I theta, here I'm going to take e to the minus theta, you're basically picking a path of the random walk. Anyway, this is just the binomial theorem. Okay, so now we want to apply it. So instead of x, we're going to, before we apply it, we want to take real parts. So x is a real number here. It's cosine theta. But here we have various complex numbers. But when we take real parts, the identity is still going to be true. So x to the t is sum over k. Probability of, so the k here goes from minus t to t. Probability of st equals k times, and let me emphasize, st is just simple random walk on the integers. And when I take real part here, I just get cosine k theta. And of course, this is just qk of x. Okay? So now let's take this identity of numbers and plug in the matrix P. So we get P to the T is the sum, probability st equals k, qk of P. Now, there's an issue here. So since I want k, observe that cosine, I can put in, I want to put in absolute value here. Cosine k theta doesn't depend on sign, but these polynomials, I want to have a positive index. So I'm putting q absolute value of k. Now here k goes from minus t to t over only numbers that have the same parity as t. And it doesn't matter, OK, probability st equals k. OK, so this is the identity we want to use. And now we just, so what can we say about qkp applied to the points a, y? So we already wrote this is 0 if k is less than the distance. But in general, it's at most 1. Because this we can write as take the Dirac mass at A. So this is just the indicator of A. You apply to that, and OK, so I want to take A, qk, P delta y. So if you look at this inner product, remember, qk of p is symmetric, so it doesn't matter on which side you put it. So this is just equal to that. And because A and delta y have just norm 1, if I look at the absolute value here, this is at most the norm of qk of p, which you said is at most 1. Yes?
Is that 2k minus t, e to the I?
What? Where?
E, right there, e to the I k theta or 2k minus t theta? In the binomial?
Yeah, e to the I k theta. So remember, this is simple random walk. So when you go, so it's exactly e to the I k theta. So it's because simple random walk takes step plus or minus 1, so not. Okay. So again, you can do it by writing the binomial formula and rewriting. But if you just think of this in this form, as I said, so you just write. Let's take out the 1 over 2 to the t, and just write t copies of this e to the I theta. Right? If I take a product of t copies, then
I'm going to get k times theta and n minus k times minus theta. The
t minus k times minus there.
Yeah, and so so exactly it leads. So it's exactly no. Again, if I take, so I don't take any. If you take any choice here, if you look at where does the random walk lead to,
Sorry,
it's
the
k.
difference is between pluses and minuses.
Yeah.
Okay, sorry.
Yeah, not the number of pluses, but the point the random walk lands. Okay. Okay, so with this observation, what is okay? So now, if we want to look at p to the t from a to y, so we apply this at the point ay, and we see all the terms with k, which is less than the distance, vanish. And we get, so this is at most the sum over absolute value of k bigger than the distance from a to y of the probability that st equals k. In other words, it's just the probability that if I look at simple random walk on the integers at time t, this will be bigger than the distance from a to y. And now you just use the simplest, most standard bound for simple random walk. It says there's a Gaussian upper bound known as the Chernoff bound or Bernstein bound, which says that probability that st is bigger than something is always less than. Well, because I have absolute value, I need a factor of 2, and then I get e to the minus this distance squared over 2t. So this is just the standard Gaussian upper bound for simple random walk on the integers. So although we're bounding something for a general random walk, just a basic bound for random walk on the integers will do the work for us.
So the idea is that you use the Chebyshev polynomials to move from a general case to an independent, like diffusive type case with the same.
If you like.
Okay, that's all.
Okay, so again, this is just the standard bound for a simple random walk. For those who want a reminder, you just get it by looking at the generating function expectation e to the lambda st and optimizing. So okay. So that's the Veropoulos-Karn bound, which it's well known, but should be even more well known. And some questions about this? So you see how it implies a bound for mixing. Actually, let me give you another example of an application in another realm, just to show you how useful this bound is. So, and this is a bound relating speed and entropy for walks. So think of a graph, finite or infinite, and so we're mostly, for this bound, we're mostly interested in Cayley graphs, but let's just assume the graph is regular. So as there, all pi is constant. All the degrees are constant. And let's look at the entropy of the walk at time n. So we fix the starting point. So x0 is some vertex A. We run the random walk at time n and look what's the entropy. So what is the entropy? It's just the sum over all y's we could get to, probability to go in n steps. So n is now not the size of the graph, it's just time. Probability to go in n steps from a to y. times the log of 1 over the same probability. Now we're going to bound this. I'm going to bound this from below, and so we're going to keep this PNAY as is, but use Varopoulos-Kahn for this part. So PNAY is at most, well, right, remember what PNAY was at most e to the minus distance squared over 2n. So taking a log, we get that this is at least the distance squared of AY over 2 minus log 2. Right? Just taking log here. Yeah, I omitted, we have a 2 here, so that's where the log 2 is coming from.
What happened to the n shape?
Yeah, it's still here. Invisible. Okay, thank you. And now what is this? This is just, if you look at the first part, it's just the expected distance squared from the starting point, so x0, which was a, to xn, divided by 2n. And then the log 2 is being summed times the probability distribution, so just minus log 2. In other words, the expected distance squared from x0 to xn is bounded by 2n times the entropy of x0 xn plus log 2. Okay, so this is already, it was an immediate corollary of Varopoulos-Kahn, but it's already a powerful inequality to know, very useful in theory of random walks on groups. So for instance, here is something which is not obvious, which follows from this, that if, suppose we have a graph G of polynomial growth, so it means if I look at distance n from the starting point, I have at most a polynomial number of vertices at that distance. So if I have at most polynomial number of vertices, how large could the entropy be? At most log of, right, the entropy is maximized. This, have to do this in the Technion, right? So one of the centers of information theory. So entropy is maximized in the uniform distribution. So it's going to give me a log of the size of where the distribution is supported. If I have polynomial growth, then so this entropy in the polynomial growth case is going to be bounded by some constant. This depends on the growth times the log n. So you see that in graphs of polynomial growth, here I was working with regular graphs, but it works for all graphs of polynomial growth. The expected distance squared from the starting point cannot grow faster than n log n. So if you just use Cauchy-Schwarz, you see that the expected distance from x0 to xn is at most the square root of this. So it's at most a constant times square root of n log n. So you get this kind of inequality with very little work, and try to do this directly with probabilistic methods, no Chebyshev polynomials. Well, it's hard. There are other methods, but nothing straightforward. Okay, so in the next lecture, I want to go in a little in the other direction and show that under some assumptions, like when we have a group, then actually the random walk has to escape at rate at least root n. So here we were talking about upper bound, saying that it can't move very fast, but if we have some group structure, then it can't move very slow either. So we're going to get a lower bound on the rate of escape, and also upper bounds on the mixing time, also involving diameter squared. So mixing time on any group is at most diameter squared times log n, using different techniques. And already, very elementary techniques will approach something which, one step beyond that is an open problem. Is the mixing time at most diameter squared? Anyway, times the degree. I'll say more next time.